Okay, welcome back. I just recopied this to save a little bit of space, but it should say pretty much the same thing. We were just talking about adding variable input to a fixed input and seeing what happened to total product. And we decided that diminishing marginal utility meant that as you add variable input to a fixed input, eventually output goes up by smaller and smaller amounts. So in our little example that we did up here, what's happening? Marginal product of labor was 300, then it was 400, so there the marginal product is increasing. But then it went from 450 to 350. Well, there's where it's beginning to decrease. And then 350 to 200, and 200 to 150, and 150 to 50, and 50 to minus 25. So you have diminishing marginal product setting in right here at worker number 2 in the example that I just made up on the fly there last video. So that's where you begin to see diminishing marginal product. Here it went, from 0 to 300, and then 300 to 450, but then it started going down. So you see how it just means that your total product is increasing by smaller and smaller amounts. So the marginal product is declining. Now there's one other way to think about that, and that's graphically. I don't want you to sweat this, but I do want you to see it. So I should have left a little more space in here because I want to get 2 graphs in here. All right, so on the horizontal axis, we're going to graph the quantity of labor, right? That's our variable input. And then on the vertical axis up here, we'll graph total product, and down here, we'll graph marginal product. So, total product initially goes up, this is what we tend to see, initially goes up very quickly, right? It goes up at an increasing rate, and here's an inflection point, and then it tends to go up at a decreasing rate, and then it may max out, and then it may start to actually decline. So there's sort of 3 main segments. There's increasing at an increasing rate. This is due to specialization and division of labor. This is when you create an assembly line rather than doing stuff yourself. So you see total product go up quickly, but it usually doesn't take too long until you start to see total product going up at a declining rate. That is, it's getting flatter. Right? So this inflection point, this represents the steepest slope of the total product curve. Again, you don't have to remember the math side of it, but it might help some of you. And then eventually, as you add so many workers in that it starts to get negative, your total product will decline. So those 3 sections up here would be, you have marginal product of labor increasing at an increasing rate up to 450, and then you have it increasing at a decreasing rate down to here. That's the middle section. And then it maxes out. Right, and now it starts to go negative. So now marginal product over here is actually starting to decline, and the marginal product of labor is negative. So that would correspond, right, to these couple sections. So then what does the marginal product of labor look like? Well, the marginal product of labor is actually at its peak when total product is going up at its fastest rate. And then here where it maxes out and starts to go negative, marginal product of labor is actually 0. So the marginal product of labor looks something like this. Now, you don't need to worry about the math part of it, but if it does help you, there's a relationship between this total product curve and this marginal product curve that if you've taken calculus, you might pick up on. This marginal product is the first derivative of the total product curve. So if that helps you, awesome. If it doesn't, no sweat. You don't need to put that together for our class. Just understand that diminishing marginal returns kicks in. What color should we put that in? We'll put it in green. Kicks in here at this point. So it's easiest to see it on the marginal product graph, but this is where you have the diminishing marginal product kicking in, or what we sometimes call diminishing marginal returns. Diminishing marginal returns, because as you add more labor, the marginal return on that gets smaller. So diminishing marginal returns kicks in, right, at this point right here. And it happens here as well. Right, this is all diminishing returns to an input, or diminishing marginal returns. I should be consistent. So there you go. You've seen it in the table. You've seen it graphically. Feel free to ask questions. We can talk about it some more, and also make sure you read this section in the book. It's a lot maybe at first, but it's really not that bad. So you can go back, watch the video multiple times if you need to, check out the book, and then be sure to see me if there are questions. All right, just a couple other things to talk about here. The short run and the long run. These are time periods as we think about production for firms. And it would be handy, I guess, if we had a nice, neat thing and we said, here's a certain amount of time, and anything less than that is the short run, anything longer than that is the long run. Call it 6 months or a year. It doesn't work that way. How we define the short run and the long run all has to do with whether or not inputs are variable. So the short run, by definition, is the period of time where some inputs are fixed. And the long run is the period of time where all inputs are variable. So the long run is the period of time where you can change every input and you can make it bigger or smaller or make it zero. So if your business goes out of, if you shut your business down and liquidate it and go out of business completely, what we're ultimately going to call exit the market, it means you've dialed everything to zero. That's the long run. If you have a pizza shop and you move to a bigger shop or a smaller shop, that's the long run because you're able to adjust all of your inputs. The short run is the period of time where at least some of your inputs are fixed. So you may be able to order more dough, sauce, cheese, and toppings. You might have a delivery that comes every week or twice a week. In a pinch, you could run to Tops or Wegmans, right, and grab some more supplies. So you might be able to get more inputs, pretty quickly. In terms of labor, if you are overstaffed and it's a slow day, you can start sending some people home. And on the other hand, if you get slammed, presumably your manager is on the phone seeing if there's anybody else, any other employees who could pick up an extra shift and come in. So those are all variable inputs because you can change them pretty quickly. But the size of your shop, the number of ovens, how big your cooler is, that is fixed. So we usually think of capital as the fixed input, and labor the long. But in the long run, even capital, right, even the size of your shop can be changed. In the short run, it can't. So if you have any fixed inputs, you're talking about the short run. And if the long run is the period of time that is long enough that you can adjust everything. You can move to a bit bigger pizza shop, you can move to a smaller one. And so the difference between the short run and the long run is different in different industries. If you're talking about Exxon building a new refinery, that could take years, from finding the land to environmental reviews to zoning variances to building it to getting it operational. It could easily be a decade. Right? So for them to add more capacity might be many, 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 many years. On the other hand, if you run a food truck and you want to get a second food truck, I don't know what the market for food trucks is like, but I bet if I went on eBay right now, I could find a food truck that I could probably acquire within a week or two. Right? So, I might have to, under pandemic circumstances, that will slow it down. But under normal circumstances, if I really wanted to add a second truck to my fleet, presumably I could track one down for sale somewhere, a used one, and have it operational, within a few weeks. Maybe if it has to be custom, made, then maybe it's a little longer. But still, I think it's, relatively short compared to some other industries. At the same time, if I want to get out of that industry, how long would it take me to sell my food truck? Well, depends how I price it. But if I really, really wanted to get out of the business, I don't see why I couldn't, if I priced it right, why I couldn't sell it in a month or two, tops. Maybe I could sell it in a few days or a week. So the difference between the short run and the long run varies a lot by industry. So there's that distinction. Next, I want to talk about costs. So when you produce stuff, there are costs associated with it. And we talked about output being the transformation of inputs. And inputs we divided into two categories: fixed inputs and variable inputs. Fixed inputs and variable inputs. And so this is one of the places where the vocabulary and the nomenclature in economics is awesome. Like, it's right on point. Makes a lot of sense. Do you know what we call the costs associated with fixed inputs? We call them fixed costs. And the costs associated with variable inputs, we call those variable costs. This is one place I think we did all right, in how we name stuff. And so since all of your inputs can be classified as either fixed or variable, that means that all of your costs can also be classified as either fixed costs or variable costs. So we can write an equation like this, that total costs are equal to fixed costs plus variable costs. Okay, so that part's pretty straightforward. I want to do a little bit of algebra to it. If this equation is true, what happens if we do the same thing to both sides? Well, then it's still true, right? So what if we take both sides and divide by Q? So you get total cost divided by Q equals fixed cost plus variable cost divided by Q. You can also distribute that, right? Dividing by Q is the same as multiplying by 1 over Q. So, and if you had 1 over Q times fixed cost plus variable costs, right, you can distribute that to 1 over Q times fixed cost plus 1 over Q times variable costs, which is the same as fixed costs over Q plus variable costs over Q. Fixed costs over Q plus variable costs over Q, right? Total costs over Q. Well, if you take something and you divide by Q, what do you get? You get the average, right? You take the total of something and divide by some number, you get the average cost per unit of output. And so here's how we would write that equation. Average total cost, right? Total cost divided by Q is average total cost. Fixed cost divided by Q is average fixed cost. And variable cost divided by Q is average variable cost. So average total costs are equal to average fixed costs and average variable costs. All right, a couple more things to think about. We ultimately want to know, what does the shape of this average total cost curve look like? That's the question that we're driving at now. And so we got to think about average fixed costs and average variable costs. One of these is really easy to think about. If you have a big TV, so let's say you were thinking about buying a large screen TV, and this is back in an era where there were still sports being played and being broadcast on TV. So if it's November and basketball season is picking up, and or about to pick up, there are a lot of games, right, that you expect to be broadcast over the winter. So if you buy your big screen TV, let's say that the TV is $600. That's pretty good sized TV. And you watch one game on it. What's your average cost per game? Well, it's $600, right? But what if you watch 2 games? What happens to the average cost per game? Well, it goes down. It goes down to half. Now it's only $300 per game. And what happens if you watch 3 games? Well, now it's only $200 per game. So if you think about the number of units and you think about fixed costs, right? If you have just 1 unit, right, the full cost is a fixed cost. But you go to 2 units, that cuts in half. You go to a 3rd unit, it goes down to a 1/3 of where you started, and then a 1/4, and then a 1/5, and then a 1/6. And so the average fixed cost curve falls pretty quickly. So, right, if you watch 100 games, you're like, well, that TV was only $6 per game. If you watch 1,000 games, right, then it was even less. So is that 60 cents a game? Now, maybe 1,000 games takes you a couple seasons, but you see how no, I'm not encouraging you just to watch TV, but if you were looking for some way to rationalize that big purchase, you might say, well, I'll watch a lot of games and a lot of movies, and therefore the cost per is actually pretty low. Right? So that's what happens with average fixed costs, right? Average fixed costs start high, they start at the full fixed cost, but they drop off quickly and they become asymptotic with the horizontal axis. But average variable costs don't, right? Average variable costs, actually, they may fall a little bit here at the beginning because of, they do, I should say. They fall initially due to specialization and division of labor. But as you keep adding more workers, right, we know that that total product goes up by smaller and smaller amounts and eventually gets negative. That means the cost of producing those units, the variable cost of producing those units actually increase, and then it gets steeper and steeper and steeper. So average variable cost over a long range, let me highlight that for you, right in this range right in here. Is that, the highlighting's not showing up. Let's try circling it. For a long range, it's increasing. And so this is the part that we wanted to get to. What does the average total cost curve look like? Well, we know that average total cost is the sum of average fixed costs and average variable costs. And average fixed costs in the beginning are really high, but they fall quickly and become sort of inconsequential. Average variable costs start out in the middle, they drop down, but then they increase. So when you add those together, if you thought about vertically adding, at every quantity, this plus this, and this plus this, and this plus this, what overall shape do you get? Well, you get something that looks like that, something U-shaped. It might be lopsided, but basically it falls, it hits some minimum, and then it increases. And that's what the average total cost curve looks like. So, take a gander at that in the book as well. There is one last thing to talk about in this section, and that is the idea of scale. So in the short run, your fixed inputs are your capital inputs are fixed, right? In the short run, some things can't be changed. In the long run, everything can be changed. In the long run, you can decide how big of a pizza shop do you want to have. And that gets at the concept of scale. So this is quantity of output, and these are costs. I'm not sure how that went into a circle. There we go. These are costs. So you can have short-run average total cost curves for different size operations, right? So if you're making sandwiches out of your kitchen, you might have a short-run average total cost curve that looks like this. That's kind of sloppy. Let me try that again. Let's try the whole thing. There we go. Short-run average total cost curve 1. And then you might say, oh, my business is going great. When I'm able to, in 6 months or a year, when with some planning, I want to move to a storefront, and make sandwiches out of there. And why do you want to do that? Because I can produce more output, and because I have more space, can hire more people, I can drive the cost down lower. But if you got the storefront and you only made 3 or 4 sandwiches, what would your average cost per sandwich look like? Well, it will be really high because you took on higher fixed costs, right? But you didn't spread them over a large quantity. So you might be able, with a larger shop, be able to drive that cost down lower if you produce a larger quantity of output. So that's for a bigger plant. Now, what if you what if you took over the Haffey Hall or ward? Which one is it? Well, I don't know where the kitchen is. It's in one of the dining hall. I don't know if that's technically Ward or Haffey. You get those confused. But if you took over the dining hall kitchen, you could probably crank out thousands of sandwiches a day with a whole crew of people working for you, and you could drive the cost down even lower, right? If you made a lot of sandwiches. But if you had to pay the rent or the lease on a facility the size of Lackman's Kitchen and you only made 100 sandwiches, your cost would be astronomical, right? But your short run average total cost curve for your bigger plant might be here. And the question is, can you keep getting bigger and bigger and bigger and driving your cost down lower and lower and lower? Well, the short answer to that is no. Sometimes the plant can get so big it's difficult to manage and you actually see your costs going back up. And so you might find a short run average total cost curve for some sort of massive plant that looks like this. Henry Ford discovered this the hard way when he built a plant in Michigan called the River Rouge. The plant was so massive that the costs of making the car there were higher than the costs at some of his smaller plants. His plant was so big it was actually, in a sense, less efficient because it was hard to manage. But each one of those is a short run average total cost curve because it's for a particular plant size. And so when we talk about scale, we talk about the ability for a business to choose the optimal size of its operation. In the long run, it can choose whatever size operation it wants. And it's going to choose something along the bottom of all these curves. So I drew in some short run average total cost curves. There are other ones in here as well, right? We'll do this in gray so it's not so obvious, but there are plant sizes that are sort of in between the ones we talked about, right? And so there are other, theoretically, there are other plant sizes that you could build. But the long run average total cost curve works off the bottom of these. If you were going to build a plant because you wanted to produce this much output, which size plant would you choose? Would you choose this one, plant size 4, where your costs are here? Or would you choose, this gray one that I drew in between here? No, you would choose this one, plant size 3, short run average total cost 3. That gives you the lowest cost per unit for that level of output. So in the long run, when you can choose your plant size, you'll choose something off of the bottom here. And so we call this the long run average total cost curve. And that's where we get this idea of scale. And the last thing to say about scale is that we can classify these regions. Over here, where as you get bigger and you see you're able to drive your costs down, you have economies of scale. And this is why you have some really big retailers like Walmart and Target and Amazon. They are able to capitalize on economies of scale and drive the price down. But at some point, if you get so big that you actually see your costs going up, you have the opposite. You have diseconomies of scale. And sometimes these are called decreasing returns to scale, and sometimes over here on economies of scale, they call them increasing returns to scale. So this would be returns to scale over here. This would be decreasing returns to scale. It's also possible that your long-run average total cost curve is kind of flat here in the middle. And in this section, you could have constant returns to scale. And so this long-run average total cost curve helps explain why firms in different industries are different sizes. In terms of building commercial jetliners, how many companies make commercial jetliners? Well, really just a few, right? Boeing, McConnell Douglas, Airbus. There are some others that I'm not thinking of right now. But the fixed costs of building an airliner are massive, right? There are huge fixed costs, and so there are significant returns to scale, significant economies of scale. And so the market is met with just a small number of firms making these planes, and they capture these economies of scale. In other industries, the economies of scale are not so great. Like with pizza shops, does each town have one massive pizza shop that serves the whole town? Well, no. We have a lot of small pizza shops close to where people live and want to buy pizza. Pizza is fairly perishable. It's good to have it hot and fresh. And once the shop gets so big, you probably get in each other's way, and it's actually harder to get the pizza and the wings to come out at the same time. So they tend to be smaller. And then what about restaurants? There's a range of restaurant sizes, but there are very few restaurants, that serve just 8 or 10 meals a night. And it's pretty challenging to run a restaurant, that has 800 tables, right? To expediting in the kitchen to get everybody's appetizer and drink out at the exact right moments for that whole table is difficult when it gets that big. I know there are convention centers that do manage to feed 1,000 people at a time, but those are special situations. Restaurants tend to be somewhere in between. So the restaurant industry might be one where we think about there's a range where there are constant returns to scale. You have some smaller restaurants and some larger restaurants, but we don't usually have restaurants with 1 or 2 tables or restaurants with 1,000 tables. Why? Because the cost would be higher in those situations. So there you go. That is your quick overview of production and costs and scale. If you guys have questions, I'm happy to talk about that. I do want to make sure you take some time and look at the book to back this up, and then there'll eventually be homework for this as well. So you guys take care. I hope you have a great weekend. If you